Hello, my name is Sean Lawrence, and this is my final project presentation for machine learning with Dr. Yang Wei. I'm going to be discussing my study on action space optimization. So, to understand action space optimization, I have to lead with some background info. We'll first delve into what an action space is, and it's also crucial to understand why we should look to optimize action spaces for machine learning models. So, let's begin. An action space basically encompasses all the potential outputs a model can give. It refers to the outputs an LLM can generate based on a provided input. These outputs can be words, phrases, or even more layered responses. Model efficiency and performance could significantly could be impacted significantly by how large and complex an action space is. Larger action spaces are often used to train large language models, since these models have to decide between millions of combinations of words, a bit just based on context. And that can make the action space much more computationally complex and expensive. In environments with large action spaces, identifying and focusing on viable paths while eliminating non-viable paths can significantly improve learning efficiency. But for the sake of this experiment, we decided to examine the action space of a smaller model, since the sheer size of the action space of a LLM would take much too long to process. So I briefly touched on this already, but it's important to consider why optimizing action spaces is important. And as the number of potential actions increases, the search space grows exponentially, making it difficult for models to explore and learn effectively. So by optimizing the action space, we can reduce the dimensionality and make the learning process more manageable. This also improves the model's ability to properly explore its environment. As the non-viable paths are pruned, it's more likely a model will go down a viable path. So now let's discuss the methods we used when optimizing the action spaces, starting with reinforcement learning. In RL, or reinforcement learning, the model receives feedback in the form of rewards or penalties. We used rewards in this case, dependent on how it responds. The goal of the model is to achieve the maximum number of rewards, allowing it to fine-tune its responses in a way that is most relevant to a given situation. Having a feedback loop like this would allow the model to find the proper path, and that can lead to a desired outcome. Similarly, we use the genetic algorithm, which is, as the name states, an evolutionary-like method that can be integrated with models for optimization. It mimics natural selection in that multiple solutions are generated over successive generations, but only the stronger ones survive in the next generation. So in essence, it's survival of the fittest, as the genetic algorithm name suggests. So compared to other approaches, the genetic algorithm is a little more robust, since it's constantly looking to refine a set of actions that a model can take. So we decided to leverage this algorithm to optimize action spaces, which brought its own set of challenges that we'll discuss a little bit later. So as for the results, I conducted one test where I had a prompt and generated a response using the model based on that prompt. Then I had another script that did the same thing but pruned the non-viable paths. So we were comparing them in that way. This is done for both the genetic algorithm and the reinforcement learning. When training without pruning, the response accuracy was not very high, and the time it took to generate the responses was also relatively long for both the genetic algorithm and the reinforcement learning. I used a calculation of coherence that I found. So it calculates the log probability of the generated text given the prompt using the pre-trained model to indicate just how the model is performing. When the log likelihood value is higher, it indicates that the coherence is more. So the average coherence value was 0.78 for when we didn't prune any non-viable paths. So that indicates that most responses were not related to the prompt. So let's compare this to when we pruned non-viable paths for both the genetic and reinforcement algorithms. So this was accomplished by limiting the number of tokens based on the coherence level, uh, whether it was lower or higher than a certain threshold, which we defined as 0.95. We saw significant improvements in the coherence as well as the time it took to generate the text. The coherence level rose to an average of 0.94, which is pretty close to an accurate response. For reference, the prompt, say we have a prompt once upon a time, and the response or completion is there lived a king named Arthur. So once upon a time, there lived a king named Arthur. The coherence level would be around 0.99 since the response is related to the prompt pretty uh, closely. So overall, there seemed to be a pretty decent increase in action space efficiency for both algorithms, although I would like to add that the genetic algorithm took much longer to train in all cases compared to the reinforcement learning. So now that I've gone over our findings, I'd like to discuss some technical challenges that I experienced when conducting this experiment. So the first challenge that I touched upon earlier was the large language models. Uh, they're really huge, they're extremely vast. So the potential paths are too large to retrieve in a reasonable amount of time. So I decided to fine-tune the GPT-2 LLM with a smaller data set, which essentially reduced the action space size. And another issue I ran into was the sheer amount of time the genetic algorithm took during the training process. At one point, the program gave an estimate of about 360 hours to complete the training process in all generations. To combat this, I ended up reducing the number of generations to a constant number of 40, which ended up significantly reducing the amount of time needed to train the model with genetic algorithm. And lastly, when fine-tuning GPT-2, I ran into an issue where it took far too long to conduct the fine-tuning. So I decided to switch to a different device with a GPU. I have a MacBook as well. So in general, GPU has a higher throughput, better simultaneous processing capabilities, and just you're able to train a lot faster, is what I've heard. So this project brought its fair share of challenges, of course, but I ultimately learned a lot from it, I think. So that's my presentation, and thank you very much.